Good afternoon, everyone. Good afternoon. My name is Mike Nicholson. I'm the Development Director here at Selwyn College, and it's a great pleasure to welcome you here and to the Quarry White House Auditorium. Before we start, just one or two housekeeping things. I know on Alumni Day, you often go to multiple events, so if you do need to slip away before the end of this event, please use the door on that side. We'll keep that open. Deepak's talk will last approximately 45 to 50 minutes. And then for those who can stay, there will be a 10-minute Q&A at the end there. But this event will finish at 3 o'clock. So I'm delighted to welcome my colleague, Dr. Deepak Venkateshvaran. And he's the, as you can see, Director of Studies in Physics here at the college and at the Cavendish here in Cambridge. And Deepak unusually is a very accomplished musician. And today he'll be calling upon his skills as a musician and obviously his knowledge as a physicist. So here to tell us more about harmonic drums, ladies and gentlemen, please would you welcome Dr. Deepak Venkateshvaran.
Thank you, Mike. So welcome, everyone. It's wonderful to see everyone here. As Mike said, I'm based here at Selwyn College and at the Cavendish, but today's talk is not on my research. It's on a pet interest of mine on the side, which is the Indian Tabla. So as you can see over here. So I've called this talk Harmonic Drums, and I'll tell you a little bit about the construction of these drums. I'll tell you a little bit about the sound that these drums produce, the language that this sound inspires, and finally, I'll tell you a little bit about the physics of these drums, And from that point of view, so towards the end, I'll talk about the physics of vibrating membranes. And I'll also talk to you about a little story that's almost forgotten, but I'd like to revive it. And this is a story of how this instrument inspired the 1930 Nobel Prize in physics. So let's just take a look at drums in general. So here are two academics. There's Richard Feynman, as you see on the left-hand side. And Richard Feynman is sitting in front of his drums, the bongos. And on the right-hand side, you have Manjul Bhargava, who plays the tabla. And as you can see from these two different drums, Richard Feynman's bongos are basically a drum with a single layer of leather as a membrane. And the tabla is a layer of leather, that's a leather membrane, but that's loaded in the center with what you see here in black. So the construction of the drum, of course, gives a slightly different sound in each case. The bongos, single layer membrane drums. The tabla, of course, have loaded membranes here. So, of course, the construction of the drum would determine the kind of sound it produces here. And one begs the question: what happens when you strike a drum? So when you actually strike a drum, you give it some energy. Now, this energy goes into the various modes of vibration of the membrane. So, for example, if you have just a circular membrane, and you give it some energy, you've got a mode of vibration where the entire membrane moves up and down and up and down, as you see up over here. That's how you have one mode of vibration. The energy, of course, goes into several other modes of vibration. So you can have more complicated modes of vibration. For example, this one over here. So in this mode of vibration, you have one part of the membrane moving up while the other part moves down, and this oscillatory motion goes on. So the segment of the membrane that has moved up would move down, the segment of the membrane which had moved down would move up, and you've got this kind of an oscillatory motion. And of course, at some point the energy damps away, and that's why the sound also damps away. So you could have even more complicated modes of vibration of these drums. And if you were to take a look at the membrane from the top, you would find that there are some segments of the membrane which do not move, and these are called nodal lines or nodal circles. So for example, in this operation of the membrane, as it moves up and down, The region that does not move, as you can see, is the rim of the circle. Yeah, the rim of the circle remains stationary over there. If you look at this mode of vibration, you've got a central line, so a line that dissects the drum head, and that remains stationary while you have motion of the membrane on either sides. So you could picture the vibrational modes through very simple diagrams, such as this over here. So when one looks at a mode of this sort with a line in the center, it's called the 1-1 mode, because you have one line within this mode of vibration which does not move, that's in the center, and you've got a circle around which does not move as well, because that's clamped to the edges. Here you have more complicated vibrational modes. So for example, in this case, you've got a nodal line that dissects the face of the vibrating drum, but you also have two circles here. So because you have one line and two circles, you call this the 1-2 mode. So if you had two lines and two circles, you would call it the 2-2 mode, and so on. So this is how you characterize the various modes here. And when you give energy to a drum by banging it, the energy is dispersed amongst all of these modes. Okay, so you're really exciting all of these modes, and each mode corresponds to a certain pitch, or a scientific term for that would be frequency. Yeah, so each one of these modes of vibration corresponds to a certain frequency, and what you listen to is a combination of all these frequencies put together. Yeah. Now, I'll briefly make you listen to the bongos just in a bit. The recording I will play for you is the recording of Richard Feynman. So, of course, it's an amateur play, but just take a listen to what the bongos sound like. So as you can hear, the bongos sound very dull, and it has some kind of a popping noise. And that's because the frequency of all of these modes do not have an equal spacing. Yeah. So in other words, the frequencies are not harmonic. They do not share a harmonic relationship with each other. So if you were to take the first frequency of this mode over here, this vibrational mode up here, the second mode would have a frequency that's 1.59 times the first mode. The third mode would have 2.1 times the first mode, and so on. Higher order modes would have 3.5, let's say, but they're never integer multiples of the fundamental. So if you want to make a harmonic drum, you need to have every mode having a frequency that is some integer multiple of the fundamental frequency. Yeah. So the frequencies generated in drums made from single membranes are not harmonics of the fundamental, and that's very clear from what you heard on Richard Feynman's play. So with that, I'd like to move to the tabla, and I would play about 3 minutes of Indian classical concert. So the people you see here, the duo, this is Zakir Hussain, and this is Allah Rakha, arguably the finest tabla players of modern times. And I'd like you to listen to just a snippet of about 3.5 minutes or so of a concert. And I'd like you to pay attention to the sound the tabla makes, pay attention to the kind of speech that the tabla players are engaging in, and try to make some observations, which we'll talk about once we finish listening to the first 3 minutes or so.
ta ta din 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 da ga da ga ta ga ta ga din na da 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 di ga da ga ta ga ta ga di da 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 di ga da ga ta ga ta ga di da 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 di ga da ga ta ga ta ga di ta 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 din 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 da ga da ga ta ga ta ga din na da 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 di ga da ga ta ga ta ga da 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 di ga da ga ta ga ta ga din da 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 di ga da ga ta ga ta ga ta 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 di di ta ga ta ga din na ga da 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 di ga da ga ta ga ta ga din da 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 di ga da ga ta ga
So you get the idea here, right? So when a tabla player is playing, they're also speaking something, and that's the language of the instrument. Okay, so when you learn the tabla, of course, you have to first learn how to speak the rhythm before you can actually play the rhythm. And the instrument itself is fairly old, so the origins are disputed. Some say it goes back to between 200 and 300 years, and some even have evidence for its origins on the time scale of several hundred years here. Now, over this very long time, of course, the style of play has changed. It's improved. The quality of tone has improved, and so it's a very mature musical instrument if you think about it. Now, let's talk about the journey from craft to sound. Yeah, the tabla is really it's an example of really craft, which ends up as a musical instrument. As you see over here, so you start off with a block of wood, you hollow it out in the center, chop up some leather, you get circular leather skin, you then put the leather skin on, and you start to braid the leather skin so that it really sits on the drum head. Yeah, so once the leather skin sits on the drum head, you begin to apply this little black paste over here. And as you can see, this black paste is painstakingly applied. You apply a little bit, you take out a little bit, you apply a little bit, you take out. And every time the tabla player is iterating and trying to see trying to hear what the quality of sound is emerging as the loaded region is being put on and taken off. And some of the best tablas are actually those which have the best tonal quality, of course, yeah. But it's to be said that this entire process is completely, it's completely manual even till this day, several hundred years later. And it's a skill that's passed down from one, so one generation to the next of tabla makers. So a bit more detail about the design of the tabla. So what they try and do is not to hollow out the entire tabla. So they just go down about halfway. And at the very bottom, they leave the bass rough, yeah? And the bass is left rough so that when you play the tabla, you don't have a back reflection of sound from within the instrument itself. So you essentially scatter out the sound at the base. Now, what this black loaded region is really something that's not really divulged by tabla makers. There are people who've gone to India, have done research studies on what this is, and they've figured out that this is a bit of rock from a quarry close to the home of tabla makers. It could have a bit of starch in there, a bit of glue, some sort of magnetic material as well. And so you have a lot of these mixtures that go into the density of this material. And the tabla makers never divulge what they're putting on there, because that compromises, of course, the sellability of their tabla if someone were to replicate their recipes here. So the idea is that you painstakingly apply this black loaded region on the tabla so as to get the best tonal quality. So that was a little bit about how you craft the entire tabla, and you go to sound. I'd like to now talk about the origins of the language here. So you heard these tabla players, Ustad Zakir Hussain and Allah Rakha, actually speak some rhythm and play it. And I'm sure many of you have also realized that what they were speaking was what they were actually playing. Yeah, and they were iterating and talking to each other, playing a little bit. And that's really very exciting when you're in a live tabla concert. So I want to briefly introduce a few syllables on the tabla. Yeah. So for example, this sound over here is the sound of na. That's the sound of na. And this sound of na, in fact, takes at least 3 to 6 months of time when you just start learning. You just play na. It's almost meditative. But it's true. Just to get the na sound, it's not really easy. A few other syllables. So this is tun. So someone would say tun. That's the sound of tun. You've got te. The sound of te is this over here. You've got re. That's re. You've got ge. It is on the bass drum. That's the sound of ge. You've got ka. That's ka. And if you put the two drums together, you've got tha. Yeah, so tha. You've got dhin. It's similar to da, but a slightly closed sound. Yeah, and you've got many such syllables that you put together. Yeah. So when you start learning the tabla, you start learning the syllables, and every syllable really takes time to play properly. You have to get the right finger action on the tabla, the right sound, the right weight, and it's quite tedious when you definitely start wanting to play well, at least. So you have all these syllables, but you put these syllables together to form phrases, and you put the phrases together to form poetry. Yeah, that's the idea. So from syllables to phrases, and from phrases to poetry. And this is the idea of a kaida. So a kaida is a rhythmic composition comprising a set of syllables played within certain rules. And these kaidas are normally played when tabla players are going solo, in a concert. So the tabla is seen as an accompaniment to the string instrument or to a vocalist. But when the vocalist and string instrument during the concerts, now these concerts can be quite long, they can be several hours. So if they're able to just say, let the tabla players go solo, the tabla player starts to play a kaida where they're starting to build phrases in their head, putting the phrases together, building up compositions and expanding upon these compositions. Yeah. So I want to give you a few examples of these kind of compositions on the tabla. So this is a basic composition that's on a 16-beat cycle. So you've got a repeating 16-beat cycle. And as you see over here, several syllables. You count the number of syllables. It's each line is 16 syllables, so 16 beats. You have 4 such lines over here, and that gives you about 64 beats. Now these 64 beats have to sit on a meter of 16 beats. Yeah. So the way you would say this is so dha terikata takaterikata dha terikata takaterikata dhinna agena. Yeah. So that's the first line. So yeah, it's to be actually said. So dha terikita takaterikita is 6 syllables. It's a 6 beat. Dha terikita takaterikita, again 6 syllables, 6 beat. Dhinna gena, that's 4 syllables, a 4 beat. So in composing a 16 beat pattern, you're clubbing 6 plus 6 plus 4. Yeah. And then you go for the next line, which is dhati dhaga dhinna gena, dhati dhaga tinna kena. You compose this not from 6 plus 6 plus 4, but from 4 in orange, 4 in green, 4 in orange, 4 in green. Yeah. And now I mentioned at the beginning that these kaidas are constructed based upon certain rules. Now, one of the rules is that every composition needs to have a segment that's bass heavy and a segment that's a little bit bass empty. Now, I notate this by an empty circle. So the third line is ta terekete takaterekete ta terekete takaterekete tinna kena. Yeah, that's the emptiness there. And then you go for dhati dhaga dhinna gena, dhati dhaga dhinna gena. So if I were to play this, it would sound something like this. Yeah, that's I must say that's really a basic beat, so you shouldn't clap. Yeah. So we move on. So now this is the kaida, the basic phrase here. We now apply certain rules. So of course, the tabla player is doing, like I said, composing things in their head. And if you were to expand what is a 64 beat over here into a 128 beat, this is what it would look like. The rule I've applied over here is just to take the first line, that's 16 beats, and I double that. So the first line remains the same as the original composition. The second and third lines are nothing but a repeat of the first line. The fourth line is the second line of the first composition. And like I said, we apply the rule of having a segment of the composition empty. And so we have this, the fifth line being the third line of the original composition. We double that, and then we have the seventh line, very similar to the first line, and the final line is the fourth line of the original composition. So this is how you begin to expand these compositions and have variations on them. So this is a variation. Let me try and play it. So it goes like this. That's about 128 beats. You could once again expand this even further if you'd like to. You could move up to sort of multiples of 64. So a simple example of one more variation here is I just go to what was previously dhinna gena, yeah, and I just have dha with some emptiness. So the way this sounds is dha tarikata takatarikata dha tarikata takatarikata dha. Dha tarikata takatarikata dha tarikata takatarikata dha. Dha tarikata takatarikata dha tarikata takatarikata dhinna gena dhati dhaga dhinna gena dhati dhaga tinna gena. Yeah, and then so all I've done is in creating this variation was to put the syllable dha in the place of what was dhinna gena before. So as you can see, this starts to become a bit tedious when you start writing down all these syllables. But there's really no way to do this because the way the tabla was, for centuries, the way it was taught to students, the teacher would never give you notation. Yeah, the teacher would just make you sit down, say some stuff, and then you have to kind of play that and then almost memorize it. And when you go back, you have to find a way to write it down yourself. And there are numerous compositions like this, so it becomes humanly impossible to try and remember every single one of these compositions. So several teachers have invented ways to write down original compositions and also find some notation. So this was the way I was taught, where the phrasing dha tarikata takatarikata is a 6-beat phrase, and we just represent it with a mnemonic of D6 here. An emptiness would be ta tarikata takatarikata, is represented with a mnemonic of T6. You could have an 8-beat phrase, dhati dhaga dhinna gena. Because there's a bass in there, there's the arrow that goes down. If you've got dhati dhaga tinna gena, the tin over here is not a dhin sound, so it lacks the bass. So you put the arrow up. And once you've generated these mnemonics, you could start to write down variations that are much more easy compared to the ones you saw in the last two slides. So, yeah, the variations, as long as you maintain 64 beats, 128 beats are multiples of 64. That's fine. Yeah. So here that's a variation 3, where 64 is composed of 24 and 8. Yeah, and the 24 itself is composed of a 6 plus 6 plus 4 plus 2 plus 4 plus 2. In this variation over here, you've got a 6 plus 6 plus 6 plus 8. Yeah, and that's 32. And that's the way you actually put these together. So I just want to I'll try and play the entire composition for you. I'll play the original composition, and I'll perform some variations on them. So in fact, I'll go through all the variations that you see over here, all the way to variation 6, and I'll finally conclude this piece. And this is just to give you an idea of what an Indian classical tabla concert might sound like here. So let's see how it goes. Yeah, so this was basically the original composition with multiple variations. I want to give you a few more examples of what you would play on the tabla. So for example, this is a composition, 32 beats, formed of 8 plus 8 plus 8 plus 8. So it goes like dhati dhagena dhatarigata dhati dhaga tinna kena tati takena tatarigata dhati dhaga dhinna gena. Yeah, so very simple. So dhati dhagena dhatarigata, it sounds like dhati dhagena dhatarigata. Yeah, so if you play it in the composition. Okay, so now you can identify phrases. So this is a 5-beat phrase, so dhati dhagena. We've got a 3-beat phrase, dhatarikata. We've got a 2-beat phrase, dhati. A 6-beat phrase, dhaga tinna kena. And if you were to, let's say, build variations on that original phrase, this could be an example where we moved away from the 8 plus 8 plus 8 plus 8 for a 32 into a 6 plus 12 plus 6 plus 8. Yeah. And this goes as, so kadhati dhagena dhatarikata dhagena dhaga tinna kena dhagena dhatarikata dhati dhaga tinna kena. And then you play the empty bit right after the first one. So it sounds something like that. Yeah, so that was the entire composition we just saw over here. Another example will follow this, but very briefly, you can identify a few phrases from the original composition. So, dhati dhagena, the 5-beat phrase, dhatirikita, the 3-beat phrase, dhaga tinna kena, the 6-beat phrase, dhati, the 2-beat phrase, the 3-beat phrase, dhatirikita once again, and dhaga tinna kena, the 6-beat phrase. So, if I were to now give this to you and say, improvise and build me something else, you would take these and try and, shuffle them around in your head and try and play them at reasonable speed. So one last example, this is it's what's called the Rajdhani kaida. It's 32 beats that's formed with a few odd numbers, unlike the even numbers you've seen. This is 11 beats plus 9 beats plus 12 beats, yeah? So the 11 beat is for dha tirikata dhagena dhaga tinna. Now if you count the 11 beats, it's actually dha tirikata dhagena dhaga tinna, which is 10 beats. So to make it 11, we just leave a note of emptiness here. So dha tirikata dhagena dhaga tinna kata, dha tirikata dhagena dhaga tinna kena, ta tirikata dhagena taka tinna, ta kena taka tinna kata, dha tirikata dhagena dhaga dinna kena. And that's what it sounds like. You just introduce the emptiness for a beat. So. Okay, so that was 11 plus 9 plus 12 to form 32. You've got a segment of 32 that's bass heavy, a segment that's bass empty, and that's why you have 64. You can identify now a few phrases perhaps already. So that's dha tirikita, our favorite 3-beat phrase. We've got dhagena, a 3-beat phrase. You've got dhaga tinna, the 4-beat phrase. You've got dhagena tinna, that's a 5-beat phrase. And if you include 3 plus 5, that's an 8-beat. So that's dha tirikita dhagena tinna. It's an 8-beat phrase. And so you can start playing around with these a little bit more. So hopefully I've given you an impression now of what the tabla sounds like. Also what the tabla, the language of the tabla sounds like. And from here, I'd like to move on to a little bit of physics and physics of the instrument, for example, and also the inspiration for the 1930 Nobel Prize. So this gentleman you see over here, CV Raman. Here, CV Raman is known for what's called the Raman effect. So in the citation for his Nobel Prize, it says he was awarded the Nobel Prize for his work on scattering of light and for the discovery of the effect named after him. Yeah, so he's known for the Raman effect, the standard effect in textbooks and in most physics laboratories, measurements are done on the Raman effect. Raman won the Nobel Prize for his work between 1920 and 1930, and he won the prize in 1930. What people don't know is that he conducted lots of studies on musical instruments between 1910 and 1920. Now, between 1917 and 1920, he was actually looking at the modal patterns of the tabla. He was trying to understand what makes the tabla a harmonic drum, unlike most other drums here. And in one of his papers, he says this. So, the musical drum stands apart in a class by itself and is used exclusively for high-class chamber music, where the noise of an ordinary percussion instrument would be intolerable. So he's referring to these drums which do not have the harmonic sound as having a very, intolerable sort of musical tone, okay? So Raman, of course, was a very famous scientist from India back in the day. And I think what really enhanced his fame was the fact that he was very well connected within the international scientific community. So you see Raman over here, and around him you see Niels Bohr, for example, George Gamow, Oscar Klein. You see Raman over here with the founding fathers of quantum theory, Heisenberg, Pauli, a few other scientists, Ewald, Millikan. And Raman was also very well connected with politics in India back in the day. So that's Nehru. And it's very interesting because there were several scientists around Raman's time. So Satyendranath Bose was one, Meghnad Saha, and they made fantastic contributions to science. They were nominated for the Nobel Prize many times, but were never given the prize. Now, Raman really was, a member of this elite network of scientists, and it was Niels Bohr that recommended Raman for the prize. But it was after Raman had asked Niels Bohr to please recommend him, So, yeah, and so I think the truth is that even till this day, to some extent, this tradition survives. Where if you know people who are within an elite network, and if they trust your work, you probably get further on than if you're a very intelligent scientist working on your own very quietly somewhere. So anyway, that's something to be recognized. So I'll take you back to the year 1920, and this is a paper that Raman had written. So that's 1920, and it was published in Nature, a very short article. And Raman calls this musical drums with harmonic overtones. When he puts a picture of the tabla, as you can see over here, and he says it's well known that percussion instruments as a class give inharmonic overtones and are thus musically defective. We find on investigation that a special type of musical drum, which has long been known and used in India, forms a very remarkable exception to the foregoing rule, as it gives harmonic overtones, as in string instruments. So Raman compares the tonal quality of the tabla to a string instrument in this paper. Now, in this little article, Raman talks about the modes of vibration of the tabla, but they've never been published here. So the question is, what happens between 1920 and 1930 for Raman to digress from publishing work on musical instruments? So to have an appreciation for this, I'd like to take you back around 120 years. The big question amongst many scientists back then was to understand why the sky is blue here. So around 1900, Lord Rayleigh answers the question, why is the sky blue? And he figures out that the sky is blue because the molecules in the atmosphere scatter blue light more than they scatter other colors. And that's the reason why the sky is blue. Let's stop for a moment and just think about this. So modern humans have been around for hundreds of thousands of years. And all of these basic questions like why is the sky blue and so on, much of quantum physics had all just come about in the last 120 years or so. It's fantastic to think about that. In the grand scheme of our existence as humans, we've really come up with knowledge that's all of modern knowledge is just from the last 120 years or so. Okay, so around 1917, like I said, Raman was studying musical instruments, published a few papers. In 1920, he puts the paper out in Nature. That's the incomplete publication on the harmonic drums. Now, in 1921, Raman travels by ship from India to England and meets Lord Rayleigh in Oxford at what was then the Oxford Congress, a scientific meeting of scientists from around the world. And Raman was, of course, on the ship for several weeks traveling to England, and he was looking out into the oceans of the Mediterranean, for example, and he found that the oceans seem much darker in blue compared to the sky. So when he arrives in England, he asks Lord Rayleigh, so can you tell me why the oceans look deeper blue than the sky? And Lord Rayleigh just dismissed him and said, it just looks blue because it reflects the sky. And that's the reason why if you have a cloud, and if you look at the color of the water under the cloud, it's not blue anymore. It's purely a reflection phenomenon. Now, Raman disagrees because Raman really believes that he saw the oceans being deeper blue. So in 1921, he travels back after this meeting to India, staring out, at the oceans. And he actually sees, it seems to the oceans seem to have a deeper hue of blue compared to the sky. And he starts to think about why this might be. So he had a little prism with him, and he tries to look at the light coming from the reflection of the sun rays over the ocean, and also the light coming from a few feet under the surface. He's trying to look at these two and trying to really understand whether he's right or whether Rayleigh was just right in saying the oceans are blue because they reflect the sky. Raman starts to build up a theory that perhaps the oceans look blue because you have an interaction of light together with the vibrational modes of the water molecules in the water. And when he arrives in India, he shoots off the second paper, a very short article, once again, to Nature magazine. This is 1921, and he calls this article The Color of the Sea. And in this article, he tries to argue why he thinks Lord Rayleigh was not entirely correct in saying that the oceans are blue because they reflect the sky. And he details his arguments for why there might be light which interact with water molecules, and that could be the effect for why the oceans look blue. And he's very excited. Now, as you see over here, you never see this these days, but the address on this article is the Bombay Harbor. So it's almost as though he arrived in India several weeks after this long ship journey, and then kind of, sent off this article when he just arrived. And this was a ship, in fact, that he had traveled in. It was a ship that I think even took cargo from Australia all the way to India about 100 years ago. So anyway, the reason why Raman was thinking about vibrational modes of molecules and light interacting with them is because of this decade of research he was doing on musical instruments, where he was trying to understand how strings vibrate, how drums vibrate, and he knew about, for example, the wave nature of vibration. And this is understood amongst most historians who've studied that era. They all seem to believe that Raman's early fascination with acoustics became the basis of his insights into the nature of light, especially his ardent support for waves theory. So the wave nature of light interacting with water molecules to generate a certain effect. So I'll take you back on this timeline. Remember, so like I said, much of modern knowledge is fairly young. The birth of quantum mechanics could be zeroed in on the time around 1925. The fact that matter has a wave character was something discovered around 1929. And Raman finally in 1930 wins the Nobel Prize. And I would say he wins the Nobel Prize for answering this question: why does the ocean water look blue? Unlike the question that Lord Rayleigh had asked, which was, why is the sky blue? And the reasons for why differed quite a bit with what Lord Rayleigh had said. And the explanation was based upon the nature of light interacting with molecules. Now, it must be said that much of Raman's work came from several experiments in that decade from 1920 to 1930, but he studied all sorts of phenomena where light interacts with molecular systems in liquids and so on. But the seed was sown on that ship ride when he's traveling to England and traveling back. And the inspiration for thinking along the lines that water molecules begin to vibrate on account of interaction with light seeded from his experience with the instruments that he was studying. So it's a fantastic example. To some extent, I fear this has been lost right now, but discovery in science really has something to do with one's cumulative life experience, and that's something which one must value. 1930, the fanfare is over. Raman wins the Nobel Prize. 1935, he comes back and publishes what he had studied on the tabla about 15 years earlier. So he gathered lots of data on the vibrational modes of these of the tabla drums, and he publishes a paper in 1935 with all the data that he accumulated pre-1921. And this is the article, 1935, as you can see over here. Then Raman does some very elementary experiments where he sprinkles some sand on the tabla drum. He tries to excite certain vibrational modes of the drum, and he tries to, build a map of where the nodal lines are. Like I said, these are the lines which are not moving as the drum head is engaged in that vibrational mode. And Raman, draws up a few modes based on his very elementary experiments. Now, what you can see in these numbers is why Raman suggested the drum is harmonic, because the frequency of the first mode, let's say that this is the frequency, if normalized, is 1. The frequency of the second mode is 2 times the first mode. The third mode is 3 times the first mode. The fourth, is 4 times the first mode. And Raman seems to say that all the modes of the tabla drum are harmonic. They share a harmonic relationship. In other words, the distance between each frequency is the same. This was 1935, and it remained fairly uncontested up until about 20 years ago or so. Now, this is what I'm aware of. There may have been other studies, but I'm aware of this study about 20 years ago, where someone had looked at the frequencies of the drum. Yeah, so for example, this drum I'm playing on is tuned to 493 hertz, that's B. And this work shows that when you excite the sound tun, which is this sound here again, tun, you're exciting all of the modes on the drum. So you excite this frequency over here, that's the the fundamental. You excite higher order frequencies. When you play the sound na, as you can see, you've completely suppressed the lowest frequency. That's just over there. So the sound na is this one. You can hear the sound na is quite different from the sound tun. And the sound tun sounds a bit lower as well. Now, the reason why the sound na suppresses the fundamental mode is because of the position of the ring finger, which sits over there to initiate a nodal line across the surface. Yeah, so purely by doing this, you're suppressing mode where the entire drum head moves up and down, because your ring finger is sat over here, which initiates a line which remains stationary. Yeah. Now, that's very interesting, because if you were to ask any tabla player why they play na the way they do, they wouldn't actually know. At least most of them who I've asked didn't really know. And Raman in some sense was coming with a foresight, saying the tabla is harmonic, but the truth is the sound na is harmonic, because the frequencies you see over here, the second, the third, the fourth, the fifth, are all equidistant. But if you were to include the sound tun, the frequency or the gap between the first and second frequency is slightly smaller than the gap between the higher order frequencies. And so the sound tun is actually not harmonic here. So when a tabla player is playing, they normally put their finger where they do over here, and they play the sound tun only sporadically. So that is the na sound is what is harmonic. Yeah. Now, much later, there have been several other studies on the tabla. It turns out it's very difficult to properly model the tabla. Yeah, you can model it using some approximate methods, but the numerical methods that were done confirm this. They confirm that the relationship between the different modes of the tabla are not harmonic if you were to account for the first mode, and you have to suppress the first mode to get the harmonic sound for na here. So, of course, I mean, tabla makers like this happy lady over here, who's trying to put the black loaded region on a drum. The question is, how did they build masterpieces? Because they have no idea of the underlying maths. They have no idea of the physics of vibrating drums. They've just been taught, do it this way and try and tune the sound to get the harmonic, so a tonal quality that's quite pleasing on the ear. And the reason why they're very lucky is because the various parameters, like the density of loading, the amount of loading over the surface of the head, there is an element of fungibility there. So you could, for example, go a little bit higher in density of the black loading region and a little bit lower in radius, for example. And so the band of parameters is this band over here that's seen in dark, and you could have some reasonable amount of play. And that's the reason why even very uneducated people can just take craft into a masterpiece, yeah, such as this over here. So, to keep in mind, harmony of sound arises from the rich underlying physics, solved using a very, very approximate mathematical model. So this brings me slowly to the end of my talk. One question I get asked a lot is, why do tabla players make these faces? And if you were to attend a tabla concert and you were to see a good tabla player go solo, and they're playing all sorts of rhythmic structures at very, very high beat rates, they always do this. And I would argue that this is a state of non-thinking, because just as you speak to your friends and family in your mother tongue where you don't think, Yeah, and the language just flows because it's quite natural to you. The language of the tabla also comes very naturally to most of these tabla players. They're not really counting in their head the sequence of numbers that will total to 64 or total to 32. And this is basically just, I don't know, the face of what some people call flow, which is a very pleasurable state where you're allowing inspiration to just flow through you. And yeah, this is a quote from a nice book I read recently, which is: the state of peak performance is a state of non-thinking. And I would argue this is both the state of peak performance and the state of non-thinking. So with that, I come to the end of the talk. This is my summary slide. I just want to leave you with one message, which is: the next time you see two tabla players talking to each other, remember that there's some numbers, some sequence of numbers are being added in their head to total to a multiple of 16. So in this case, 7 plus 8 plus 9, that's 32. But they don't speak the numbers out. They speak the language of the tabla. So dhati dhage na dhatarikita. And then the next tabla player picks up on that. They are not counting the sequence of 32 as 7 plus 8 plus 9 plus 8, but as 6 plus 6 plus 6 plus 6 plus 8. Yeah. And they would say something like dhati dhaga tinakena. Yeah. And they do this at about 320 beats a minute, purely from muscle memory. And what they don't know, and I've asked everyone this question, including my own tabla teacher, and they never have a clue why they put the ring finger where they do. Yeah. And that's the knowledge which all of you have today, is that you put the ring finger over here because you want to suppress the fundamental frequency, because that fundamental frequency is not in harmonicity with the higher order frequencies. So the only way to really get that sweetness of sound is to position the finger or where you do. But this style of play has evolved over years. So the ring fingers are positioned to suppress the fundamental vibrational mode to ensure harmonic sound, but they're often unaware of it, but you are right now. So with that, I'll bring this talk to a close and I'll take any questions.